Hey, what's up? Welcome to the sexiest channel on YouTube. So, today we're going to talk about reference frames and displacement. So, what is this, right, in physics? There you go. So, as you can see, I have my beautiful whiteboard right here. So, let's go. We have reference frames. So, reference frames. What the hell is this? What the fuck is it? Sorry. What is this? So we don't know, right? So basically, reference frame, sorry, are basically the. It's a very important It's a very important concept in physics, and let me explain why. So we already. So, for people that don't know, everything in the universe is going through kinematics. Everything basically through motion. Everything is moving. Kinematics is just the fancy physics way of saying motion. So everything in the universe, or the known universe, because it's probably much bigger, um, is moving. It's constantly moving. And in kinematics, we just care about how things move. So if a planet or some object is moving through space, we just care about how it's moving. We really don't care about why. Like, why is this thing moving? Like, what made this thing to move? In kinematics, we don't care about that. That is another thing that's called dynamics, and it's actually about the forces that influence, in this case, this object. But right now, we just care about the how. So how things and how stuff moves, how objects move in the entire universe. So basically everything in the universe is in certain motion, if we can say it that way. And basically here's where we are like, okay, if we want to do physics about, I don't know, this battery, or I mean, this battery doesn't make that much sense. Let's say a car. So we want to, I don't know, measure the velocity of a car or whatever. Uh, I mean, I'm just gonna draw a Cybertruck because that's very easy to draw. There you go. So here's our Cybertruck. So here's our car. We want to basically know what is like the motion of this object. But remember, everything in the universe is moving, so how are we gonna really know the motion of this object if the entire universe is moving? Like, how are we gonna cut all the signal, sorry, all the noise, and just focus on this little car in the universe? Well, that's why we have reference frames. So basically, reference frames is for us to for allows us to know the motion of this car. So obviously, a car is on Earth. So let's say this is Earth. This is America, Mexico, whatever. This is Earth. It's moving, right? So the reference frame in this case will be Earth, right? As we know, Earth is also moving around the sun. So it's moving, right? Yeah, everything's moving as I said. But in order to know the motion of this car, we're gonna get the reference of the environment in which that car is placed on, which is the road, which is basically Earth. So in that case, even if Earth is moving, we don't care about that. We just put our point of view, if we can say it that way, on Earth to see how the car is moving. And that's basically our reference point. In this case, our reference point is Earth. And that's gonna allows us to know the motion of the car. I think a great example that is gonna really sink in is basically a train. So we have a train, we have a moving train, and then we have beautiful windows on the train, and then we have a person on the train that's walking. So basically, this person is walking but the train is also walking. I mean, it's not walking, it's going through speed. So this person, this object, this person, this human being has a speed, and this train also has a speed. Well, in this case, obviously depends what we want to measure in motion. Like, do we want to measure the motion of the train or the person, or what are we going to do? So let's say we want to measure the motion of the train. So if, like, let's say our reference point is the same as the Cybertruck, so Earth is our reference point, then we're gonna know, so I don't know, how the train is moving through Earth, right? It's going through Earth. Now, if our reference point was this man right here, sorry, if this man right here was a reference point for the train, then the train is not moving at all, right? That's what happens, right? When you are on a train, on a moving train, or in your car moving, it seems like the car is not moving, but rather it seems like the earth is moving. Seems like the earth is moving, or no, for example, the trees seems like they're moving, right? But that's not the thing. Like, in reality, the train's moving. Whatever, you get the point. So, yeah. Now, if we want to know what's, for example, the speed at which the person in this case is going through, okay, our reference point will be the train. So if our reference point is the train, then we can know at what speed the person is going through. Now, we could also do something very interesting, which is the speed of the person relative to the Earth, or in this case, with the reference frame of Earth. Instead of the reference frame being the train, in this case we have the reference frame of Earth. In that case, this man is going super fast, because we are combined, because he's basically going at the speed of the train plus his speed. I don't know, speed. Human and train speed. And that's, well, lots of speed. So yeah, that's basically the usefulness of reference frames. It's just very useful for us to distill and cut off all of the noise of the universe and just know what's the motion of a certain object, and that's super useful. In the case of displacement, what is displacement? Well, displacement is basically what's the delta meaning change, between the starting point and the end point of an object. So we know that when an object moves, it has a starting point and a final point, if we can say it that way. So the train, let's put that example, is gonna move, right? If it moves 1 millimeter, well, has this starting point where the train move, this other point, and I mean, is 1 millimeter. So it's not that much, but it's still something. If we could go on to micrometers, and it's still moving, okay? The thing is that it's moving, and every object that is moving has basically two things. In this case, we have the distance, the amount of distance it moved, in this case 1 millimeter. In physics we call this how do we call this in physics? Sorry, in physics we call this a magnitude, right? The fuck? I mean, yeah. So sorry. In physics we call this magnitude. So it's a fancy way of saying, hey, this is 1 millimeter. You know, the magnitude. Here's the magnitude. Okay. Oh, sorry. Fuck. Sorry, I'll no longer have battery on my Apple Pencil. Whatever, I'm gonna explain it with my hands. So in physics we have, okay, so we have this initial point of the train, final point of the train. The distance is basically the magnitude. And then we have also another thing, which is the direction. Direction. What's the direction? Is it going east, south, north, and or west or whatever? And in that case, that's what we call a vector. So a vector in this case has magnitude and and direction. Okay. Now, what are vectors? What is that really? Well, vectors, I mean, there's formal definitions for it, but I could define it as a mathematical expression in which we represent motion in the universe. So it's basically how we humans figured out to mathematically explain motion. So this apple that I just ate, when I do this, it went from point A to point B, and in that amount of time, it moved a certain distance, in this case the magnitude, and then it moved at a certain direction. In this case, it was to this side. So, well, in my point of view, to the north. So that's a vector. And it is more represented like an arrow. So we have a vector. So basically, when you see an arrow pointing to this direction, it's basically saying, hey, this object is basically having a motion to this to the north and has this magnitude and whatever. So that's displacement. And I mean, I just said two concepts in one, displacement and vectors, but basically displacement is a vector, right? And vectors are very useful for literally measuring any motion in the universe. So right now we are simplifying to one-dimensional measurements, like left, right, and that's it. Obviously, we can then go left, right, up, and down in measurement, and that will be two-dimensional. We can go then left, right, up, down, up and bottom, or include the depth, and in that case, that will be three-dimensional. But that's another topic. Basically, displacement is the change in what was the change from the object from position 1 to the final position. Sometimes there's some crazy stuff that happens where this is the initial position, it goes and does all of this, final position is the same, and in that case the displacement was 0. There was no displacement. Now that's not the same as distance. The total distance in this case was all of this, but displacement is just the initial position minus, final position minus the initial position. Okay. Vectors, as I said, very useful for measuring motion mathematically, and they have magnitude and direction. In the case of reference frames, they're very useful to know, basically cut the signal, all the motion that is happening in the universe, and just concentrate on one object. And yeah, that's basically reference frames and displacement in physics, which are the foundations of kinematics or motion, which is basically how stuff moves in the universe.